Yes. So in this session, we are going to discuss about the curve fitting to a bivariate data. In a bivariate data, all we know that there consist of two variables. One is the independent variable, another is the dependent variable. Now, there is a particular method by which we can find a best fitted curve to the given bivariate data in your in the statistical problem, right? Say, for example, in a bivariate data, if I am going to plot the values of the data, then there will be x1, y1 somewhere over here, then x2, y2 over here, somewhere here, say x3, y3. And likewise, we are plotting the data like up to x and yn. Okay. So now what we need to do is, after plotting this bivariate data, we will be getting some scattered points. They are not in a linear manner, or they are not following uniformly. We are getting the data in a scattered manner. This will also be known as a scatter diagram. The diagram that will be obtained out after plotting these bivariate points in the xy plane. The scattered the points will be in a scattered form, so it is also known as, this diagram is also known as the scatter diagram. Now what is our mention or our target over here is to fit a best curve, or to draw a best fitted curve to these scattered points. Say, if I'm getting this as the best fitted curve to this scattered point. So what I need to have over here, best fitted curve means it should maintain a minimum distance from each of these scattered points. Let this curve, whatever we have fitted over here, let this curve be fx. Then corresponding to each of the points x1, x2, xn, each of the independent variables x1, x2, xn, the corresponding points on the curve will be fx1, fx2, fx3, likewise fxn. Okay, so now what I need to do is I need to make a minimum distance from each of these scattered point to the particular curve, from each of these scattered point to this particular curve. And we need to minimize this distance. So first, let us see what this distance is actually. So if I denote this distance as, say, d1, then d1 from the point x1, y1, then d1 will be y1 minus fx1, right? Similarly, if I write d2, what it will be? Y2 minus fx2. And likewise, if I go, if it is a n point data containing n entries, then the last one will be yn minus fxn. Now, what is our target? This is a distance. Now, this distance may be, sometimes it will be positive. We may get a positive quantity, we may get a negative quantity. So to overcome this difficulty, what we need to do is we need to take the squares of these distances. That means d1 square, d2 square, d3 square, dn square, like this. And then we are going to sum up all these squares, and then we are going to minimize the sum of all the squares of distances. Okay, so I'm denoting capital D as sum of the squares of all distances, like d1 square plus d2 square plus d3 square. Likewise, it is going on up to dn square. Now, what is our target? Since we need to get a best fitted curve with these scattered points, in these scattered point in this xy plane, so that best fitted curve will maintain a shortest distance between these, among these points. Okay, so that means we are going to minimize the squares of the distance. That means here our target is to minimize capital D. Our next target is to minimize capital D. Minimize capital D. Okay, so now minimize capital D means minimum. I need to take the minimum of capital D, means sum of all di squares. Now what I can write the di as, it is minimum of summation over I varying from 1 to n. What the di is? Yi minus fxi, right? So fxi is the curve. So this is the target. This is how we are going to obtain the least fitted, best fitted curve among the scattered diagram or among the scattered point, whichever is given to you in a bivariate data. Now we need to think about the curve. If we are going to fit a straight line, then we need to write accordingly our fx. If we are going to fit a parabola, then our fx will be changed accordingly. So in this case, I'm going to fit a straight line to these scatter diagram or to these bivariate data, right? So if I'm going to fit a straight line, then my fx will be equation of straight line. Let it be ax plus b, where we can say a is the slope of the line and b is the intercept of the line. Okay, so I'm replacing fxi with axi plus b. So now we are going to minimize. Actually, we need to minimize summation over I varying from 1 to n yi minus axi plus b. We are going to minimize summation over I yi minus axi plus b, right? Now, since in this minimization, what are our unknowns? A and B are the unknown quantities. So what we need to do for minimization? We need to take the derivatives with respect to A as well as with respect to B. So for minimization, I need to take del A of, let it be capital D1. This minimization, I'm denoting it as capital D1. So del A of capital D1 equated to 0. And then again del B of capital D1 and equated to 0. Now utilizing these two equations, we will be getting some equation in terms of A and B. And then we need to solve for the values of A and B to get the regression line. That is, or you can say the best fitted line, fx equals to ax plus b. The line will be ax plus b, right? So let us move on further to take the derivative, to equate the derivatives with respect to a and with respect to b to be equal to 0. So I'm moving on for the next for the continuation part of the whiteboard. Let me move on. Let me clear this. Yes. So from here, what I need to do is del A of D1. What is our D1? Del A. Minimizing we need to D or del A of D equals to del A of summation yi minus axi plus b whole square. Axi plus b whole square, right? And they equate it to 0. So let us see what will come out from here. So summation obviously over I varying from 1 to n. So differentiating with respect to a, we will be getting it as 2 times of summation over I yi minus axi plus b. And since we are differentiating with respect to a, so minus xi will be the coefficient. So it will be minus xi, and that is equals to 0. Now after simplification, what will come out? 2 will be gone with a negative sign. So we are coming out with summation xi yi minus a summation xi square plus minus obviously minus b summation xi equals to 0. So the one of the equation that we will be getting it as A summation xi square plus B summation xi equals to summation xi yi. Obviously, summation is taken over I, where I varying from 1 to n. So this is one of the equation we are getting in the with the unknown quantities A and B. Now what else? This is with del A of D equals to equating to 0. Now next, if we differentiate with respect to B and equate it to 0, what happens? Del B of summation yi minus axi plus b whole square equals to 0. So what we will be getting it as, differentiating with respect to b means only it will be coming twice summation over I yi minus axi plus b with a negative sign equated to 0. So 2 and the negative sign will goes off. So we are left with summation yi minus a summation xi plus, minus b summation over I 1. So if I sum up a 1 to n times, as I varies from 1 to n, 1 plus 1 plus 1 n times, so we will be getting it as n. Okay, so ultimately the equation will be summation a summation xi plus bn equals to summation yi. So this is the next equation that we are getting. Now with these two equations, solving the values of A and B, after getting the values of A and B, utilizing these two equations, we will be finding the unknown quantities A and B in the regression line fx equals to ax plus b. So in this regression line, A and B are unknowns. We will be getting these unknown equations from this particular equation 1 and 2. Now equation 1 and 2 consecutively, togetherly known as the normal equations. Equation 1 and 2 togetherly known as the normal equations. Normal equations. Now what we need to do is, here we have selected, or here we had made the target to a straight line to be the best fitted curve to the given bivariate data. Now, instead of straight line, if we are going to fit a parabola or if we are going to fit any other curve, then accordingly, the equation of fx will change. The curve equation, as I have taken the target to be a straight line, so I have taken the equation as ax plus b. Simultaneously, if you target your best fitted curve to be a parabola, then your equation will changes to x square plus bx plus c, which is the general equation of a parabola. So likewise, this is the method of least squares, which will allows us to find out the best fitted curve in a bivariate scattered data. Or rather you can say, from the bivariate data, we will be getting, by plotting the bivariate data, we will be getting a scatter diagram, and we are getting a best fitted curve to those scatter diagram. Now you can say that in the beginning, I told you the method, this whole method is known as method of least squares. Now I think after covering out the total part, you are in a position to make the sense of the name that suggests. What the name suggests, that this is the method of least squares. Why this least square, method of least squares? Because we are finding from the scatter data, as you have seen while going through the method, actually we are finding the minimum of the squares of the distance for each point, squares of the distance of each point of the bivariate data from the best fitted line or the best fitted curve. So first we are getting the distance, then we are squaring that distance, and then we are taking the least of that distance, least of the sum of that distance. And that's why the name suggests as method of least squares. So utilizing this method of least squares, we are obtaining the best fitted curve to our bivariate data. So that's all how we are going to, this is the part where we have uses or where we have considered straight line to be a best fitted curve to our bivariate data. Now in my next session, we will be considering a parabola to be our best fitted data, and then we will see that what will be our regression, what will be our normal equations rather, and utilizing those normal equation in the further sessions, we are going to solve out the problems where a bivariate data will be given to us for a particular real life problem, and we are going to find a straight line, we are going to find a curve utilizing the normal equations, which straight line or which curve will be the best fitted to the bivariate data, whichever is given to us. So that's all for this session, and we are coming with the problems in our next sessions, right?